Okay, now we're going to go into more detail on what is a rhumb line, how it works, and how it's not actually as true of a line as a great circle is. Because this is something that personally confused me a lot when I was going through terrestrial navigation, and took a long time for me to figure out on my own what it was, what it actually meant, and how it worked. As I said before, a rhumb line is a straight line on a Mercator projection, but that's not actually the perfect definition of a rhumb line. Technically, a rhumb line is any line that passes through meridians at the same angle, no matter what. So, for instance, if we had a course that looked like this, and let's say this is on course 070 true, a rhumb line, or this is a rhumb line, what this means is if we had a meridian here of like 1 east, 2 east, 3 east, whatever, at this point here where the track intersects 1 east, that would be an angle of 070. And then here, that's an angle at 070. And here, that's an angle at 070. And that's why it's so important that we use rhumb lines when we're plotting, because it's the only way you can have a straight line and you could follow it without ever having to adjust your compass along the track. Why this isn't really realistic to the actual world is because you have to remember these meridians are not actually perfectly parallel lines that shoot off into infinity in both directions. They're meridians on the Earth. That means that they all converge at the poles. So if we then imagine, let's say this is the North Pole here, you can think of every single meridian on Earth shooting out from the North Pole into all the different directions it can. When you're down in equatorial regions, they look like this because you're staring at the side of the Earth. But then if you come up to the top of the Earth, you can see them all fanning out from the North Pole or fanning out from the South Pole. So let's try to recreate this relationship here where every meridian is intersected by the track at 70 degrees. Well, let's say if we started with this meridian here, it would pass through at 070, continue on track, and here, now it has to pass this one at 070, and you can see I changed direction a little bit. Now it has to pass this one at 070, and this one at 070, and this one, and so on and so forth. And what you get is you actually spiral in to the North Pole, because every time you have to turn to a more acute angle and turn towards the pole to maintain that 070 relationship with the meridians. And it doesn't just happen at, let's say, 1 east, 2 east, 3 east. It's happening constantly because every tiny little change in difference, you're technically at a new meridian, just not a full number. So you're constantly spinning inward and wrapping towards the poles. If you had a southerly course, if you were, say, like 135, you would actually spin outwards and down until you reached the southern hemisphere, and then you would wrap in towards the South Pole. So every rhumb line, although it plots as a straight line on a Mercator projection, is actually a spiral, and those spirals are called Loxodromic curves. I don't know if I'm actually spelling that right, but Loxodromic curves. This is not something I think you'll ever be tested on, but it's an important concept to understand because without it, you'll never really see why a great circle route is better than a rhumb line route. Because a rhumb line is a spiral, and a spiral isn't a true straight line, meaning if you're trying to go from point A to point B, taking the spiraling route is not actually as direct as going along the curve, which is what a great circle does.